So Vivek is relatively new to Cornell. I know that much, and you're in civil and environmental?
Biological environmental.
Biological and environmental engineering. Okay, so one of the something PEs, and doing interesting working stuff.
That's all right. I'll start off with a description of that.
Very good. Thanks.
Thank you. So hello, as mentioned, my name is Vivek Srikrishnan. I'm a new faculty member in BE. I started in July. Came from Penn State. I do actually, my original academic discipline was mathematics. And I have since drifted into engineering, which still feels a little dirty at times. But you know, that's how it goes, right? So what I wanted to talk about today, this is sort of a broad overview talk rather than a deep dive into a specific piece of research. But I wanted to talk about climate risk management and thinking about climate impacts. You know, especially COP26 was just over the last period of time, so climate change is sort of in the news. And in particular, there's a lot of places where we really need to have a deeper collaboration and gain some interest from people who really think deeply about statistics and mathematics. And I'll try to give an overview of some of those areas where I think there's real synergy and a need to inject some ideas and some techniques and some collaborations. So first, just to start off, damages from extreme weather events are increasing. So this is from a recent paper from 2019, which shows the basically the size of the right tail area estimate of damages. It's a little complex. The main key point is that it's increasing. Right? This is the 95th quantile, the red line, and that's going up over time fairly unambiguously. So that's the extreme weather events, right? Not just the events in themselves, but the really damaging events.
Is this shit like inflation adjusted or like price index adjusted, or is that?
Yeah, it's inflation adjusted.
Okay.
So to some degree, there's somewhat of a question here. So there's some debate, for example, when it comes to hurricanes as a contributor to this, how much of that is due to populations continuously shifting towards the coast, right? It's not necessarily adjusted for that. But then if you start thinking about other extreme events, wildfires and so forth, that isn't as relevant. But with hurricanes, that is an outstanding thing about exactly what is the best way to correct for that population shift.
Sure.
Because what the trend seems to be is that hurricanes are, at least Atlantic hurricanes, are occurring less frequently, but they seem to be more intense when they do strike. And there's a good causal mechanism for that in terms of sea surface temperatures rising as part of that. The other thing is that power outages, this coloring doesn't actually show the headline from the Washington Post, but it is true that there's more and more power outages that are resulting from, again, climate disasters may be a little bit overstated, but wildfires, for example, cause rolling blackouts, outages due to hurricanes or winter storms. Again, Winter Storm Yuuri in Texas, was an example of this. And ultimately, this is sort of where the rubber hits the road, right? When damages occur, when power goes out, people start to care about what's going on in terms of weather and extreme events. Now, these are figures from the latest IPCC report from Working Group 1, so that's the Intergovernmental Panel on Climate Change. They're the body that every so often synthesizes the existing literature in climate change to represent and kind of combine the current state-of-the-art knowledge. And these figures are small, and I apologize for that, but they basically say how much of this is for these various types of events. There's heavy precipitation, flooding damages, drought. How much of that appears to be due to human-induced climate change, and what's the level of confidence that the literature has in different parts of the world based on sort of these regional case studies. And with flooding, that's not too much of a surprise, especially with sea level rise, that you can kind of directly attribute that to climate change. Heavy precipitation and drought are a little more, it's a little more indirect of a mechanism, so there's a little less confidence there. But this seems to be the trend, is that we're increasing towards more and more of these types of extremes occurring, and that happens to be occurring as the climate is warming, and there's a good theory about why there's certain changes to the jet stream occurring due to overall warming temperatures and how that manifest in terms of changing precipitation and drought patterns. So just to give an overview, what do we mean by risk? Because this is not a term that always has a standardized definition, right? Sometimes people use the word risk and they just mean probability. So when I'm discussing risk, this is a combination. There's the probability of the hazard. So what is the physical occurrence of a physical event? So what is the probability of a flood? Like that's just the hazard component. But then what matters is that if it floods and nobody lives there, nothing is there to be harmed, is there really a risk, right? What does that mean? And so it really is a matter of vulnerability and exposure, right? So how many people are exposed, or how many things that are of interest, right? It doesn't have to be people, it could be ecosystems, depending on what the system is that we care about. But what is exposed and how vulnerable is it? So if we have a bunch of houses in a floodplain, but they're elevated, right? And so there's no actual damages occurring, there's no water penetrated, then they're not really vulnerable to the flood even if it occurs. So you have to consider these sort of separate things, and again, there's sort of gray lines here, like between exposure and vulnerability. It's not exactly a hard and fast line. But these are all different mechanisms that we want to think about when we think about potential interventions, right, that might mitigate risk and climate risk. And then the last is, this is sort of, because this is a really recent paper, looking at the response, where sometimes the response can actually further compound the risk or manage the risk in some way. So there are some socioeconomic phenomena. There's one called the levee effect, which has gotten a lot of traction recently, where somebody builds a levee or a flood wall, and people feel that it's safe, and they're more likely to invest or move into that floodplain, and perhaps in a way that's disproportionate to what the actual level of new safety is with that floodplain. So this is something that we actually found talking to people in New Orleans. Once the levee was rebuilt after Katrina, they said, oh, well, we're safe for another 100 years. Right, because it goes back to a 1 in 100-year flood. So, there's that risk perception versus actual risk, and you have to factor that into account when what is the human response, because that directly affects the vulnerability and the exposure. So when we mean climate risk management, one of the things that makes us really complex, is that we have a really complex system that we're talking about potentially intervening in. So well, broadly speaking, we can classify climate risk management strategies into a bunch of different categories. There's mitigation, so that's reducing the amount of greenhouse gases that we emit. There's carbon sequestration, so this is something that's gotten a lot of attention recently about negative emissions, so sucking carbon out of the atmosphere and storing it somewhere. Location to be announced. Solar radiation management, this sometimes gets called geoengineering in the popular media, so this is the idea of changing the way that the Earth responds to incoming solar radiation through seeding clouds, or people have proposed weird things like flooding the Indian Ocean with ping pong balls to increase the albedo of that particular area. Right? You get all sorts of weird things coming up in that domain. And then adaptation is, saying in a particular locale, there's a particular hazard, how do we adjust the vulnerability, exposure, probability of the hazard? So, for example, adaptation is almost always local, right? So something like building a flood wall, elevating homes, moving away from a hazardous area. Those are all adaptation measures. Mitigation is, transitioning to cleaner forms of energy, for example. Carbon sequestration, there's direct air capture, that kind of thing has been talked about recently. And like I said, that's a whole catch-all for a whole bunch of stuff. Now, what makes this tricky is that and this sort of shows what the feedback loops there look like, how there's a link, greenhouse gas emissions are directly affected by mitigation, carbon sequestration targets greenhouse gas concentrations, and of course those are related. So these are all related components of a system, and they all sort of form an altogether portfolio of options. The problems here, though, are that there's many deep uncertainties. So by deep uncertainty, this is also sometimes called Knightian uncertainty, if you've seen it, or ambiguity. The idea is that it can't write down a single probability distribution. So for example, if I were to ask people in this room, what do you think the probability of global mean temperature will be in 2100, right? Everybody write down your probability distribution. I'm going to get a number of probability distributions equal to the number of people in this room, right? Because it's a very, it really depends on the assumptions and the sort of mental model that every individual has. There's no, consistent way to just write down a probability distribution for that. But that really has implications for how much should be mitigation versus how much should be adaptation. There are people who argue that mitigation may not be worth the cost and we should just adapt our way out of things. Right? That is an argument that people have made. There are other people who say that you can't necessarily adapt your way out of everything, but it really depends on what you think those impacts are going to look like. Another, and this is what I'll focus on a little bit more in this talk, sorry, are that there's multiple interacting sectors and scales. So, excuse me, the the impacts and the levers that you might pull to try to address those impacts occur across different sectors. So, mitigation is largely so far concerned energy and transportation, and some of the impacts occur all over the place, but then they propagate, right, and they feed through. So just because something impacts precipitation, it's not only affecting water, it's also affecting agriculture, it's also affecting energy. You knock out the energy system, and you've got implications for the water system. And so these our infrastructure systems are all so connected that it's not like you can just affect one thing. The other is that due to issues of trade and due to other compounding effects, the scales of these can, what happens in the location can impact the region, what happens in the country can impact, things on a global scale. And another complicating factor is that stakeholders have different values and objectives, once this comes back up. So you've got, a number of different stakeholders in any one of these decision problems. They all have different things that they prioritize, that they value, and that they really care about. And how to make these decisions and try to propose what these implications are across a number of these different objectives is a challenge. How do you provide decision support for that? How do you make this transparent so that it's clear what the priorities are and how things come in? So these are all the things that make this really difficult. And this is an example of how if you kind of break out the example values by different things that you might measure or that factor into different types of interventions that you might take in the case of flooding. There's different things that weigh different values. Certain things where a sense of place is what you're responding to, other things that are purely economic. It really depends on how you choose to measure things. So like I said, what I really want to focus on today is the issue of sectors and having these multiple infrastructure systems that are all interconnected. So a lot of analyses in the academic literature and even reports and things like that focus on one sector. People focus on the water system, people focus on the energy system, people focus on agriculture, transportation, but in reality, all of these are tied together, right? And not only that, but people respond to things. So there was a report from one of these climate consulting firms recently that, argue that this is the number of people who will be affected by sea level rise by 2100 or 2050 or whatever the year was. And the reality is that's not really the right number, right? Because people move, right? If you keep flooding, people don't just sit there and let themselves get flooded. There are interventions, they leave, whatever. So there are all these feedbacks between socioeconomic, engineered, and natural systems that have to be accounted for if we actually want to get a realistic idea of what these impacts look like. But the second we start accounting for feedbacks and endogenous behaviors, and especially the human and governance systems, modeling becomes very difficult. Right? How do you model these things? How do you actually parameterize things? How do you represent uncertainty properly? Right? These are all really outstanding challenges once you start to consider the connectedness of these systems. Not to mention that as you start to couple models together, especially if they're sort of high-resolution process models of various systems, the computational time starts to explode. Right? And that makes it difficult to run models frequently enough to be able to resolve uncertainties and to explore what happens over a number of different scenarios in the future, which means you're often tied to one or two guesses about what might occur in the future, and that can lead to overconfidence and biased decision making. So this is an example of an upcoming paper from Nature Energy that I was not involved in, but it's related to some of the research that I do. So this is a paper that was looking at the coupling a climate model with a water systems model, so they'll look at water balance and water temperature propagation through the system. The idea of this relatively limited study is that water temperature, so thermal plants, coal, natural gas, etc., use water to cool the plants and create steam. The Federal Energy Regulatory Commission, FERC, does not allow plants to operate if the water temperature is above 32 degrees that they would be using for cooling, 32 degrees Celsius. So if the water gets up to that point, the plant has to shut down. And so the that is what is modeled here in terms of, if the water temperature in that area is that high, the plant shuts down, and then they look at how that propagates through the system, where are the resulting outages due to transmission overloads, and what are the associated economic damages. That's sort of that full analysis to couple these things. So one thing is that this is a fairly complex thing because of the nature of how the electricity system is set up. So this is a map of a simplified version of the Western interconnection. So the United States has 3 different electricity grids which are not connected. There's the Eastern interconnection, the Western interconnection, and ERCOT, which is Texas. Most of Texas, which is not connected to the rest of the U.S. grid. And what happens is all of these, this is one particular snapshot of 1 week that's particularly illustrative. The blue dots are plants that have to shut down because the water temperature is too high there. And the red dots are where outages occur, and the red lines, which are maybe hard to see, are where transmission lines are overloaded. So that's the bottleneck. That's why we're getting the outages where we're getting the outages. And there's no real rhyme or intuitive reason why they're occurring where they're occurring. Right? A lot of the plants are out here, but you get outages, mixed in over there. And so this is actually, this is just due to how the electricity system is structured and engineered. But it means that actually trying to project where these impacts might be and what they might look like is very difficult, right, for a particular scenario. And in fact, this gets, they were able to look at a couple of different scenarios, but that's about it. So what happens if you, so again, I apologize for the size of this, if you take California, Arizona, sort of the southern part, and Washington, and replace a lot of the coal capacity with solar and wind, you get a different outage pattern and a different, pattern of where things occur. Even though the water scenario, the hydrology is the same, the water temperature distribution is the same. If you do this instead in Alberta, Washington, Montana, so sort of some of the northern and eastern areas, you get again a very different outage pattern, even though you get exactly the same hydrology. So the water temperatures are the same everywhere. But the nature of what gets turned off and where the outages occur is very different. And if you just get rid of all coal and solar, or all coal and gas and replace it with wind and solar in California, you get a very different pattern. So this becomes tricky, where we really want to be able to do these runs a lot to get a sense of what these maps look like, and maybe try to understand what these patterns look like. Where is new transmission needed, for example, to build resiliency to these types of events, to prevent these outages. The problem is this one model, if you want to run 1 year, takes 6 to 12 hours to run in total. And that gets prohibitive if you're trying to really resolve tails of risk distributions, really looking to look at a lot of scenarios. That is a problem, right? You can do some parallelization with this, but it really, actually this is with parallelization, so every week is being run independently. So using 52 cores, it takes 6 to 12 hours to run this model. So this is not a cheap model. And fundamentally, this is because we're trying to resolve the power system, which generators are on and which are off at any given time. That's solving that optimization problem. It's a mixed integer linear program, but it's a mixed integer, it's a big tree that is trying to do branch and cut type solutions with. It takes a really long time. And there's no kind of getting around that unless we can find a way to sort of emulate that response. But that's tricky because you really have to get the spatial pattern right. Right? It's not enough to just sort of get the objective function, what's the total cost or something like that right. It matters which generators are off where because of the way the transmission routing occurs. So that's one sort of challenge that exists, is how do we get around that computational bottleneck in that type of fashion. So the thing that I really want to spend more time on, though, is, I haven't talked too much about uncertainty yet. I've just sort of talked about some of what climate risk is and some of that. But what are the things that are relevant to statisticians and mathematicians, right? This is an applied math colloquium. So, I should talk about stuff related to at least statistics and, mathematics at some point. And so I've sort of highlighted 3 challenges that are most directly relevant to my work, though I'm sure there are a whole host of other ones out there depending on who you talk to. The first is what we've kind of touched on just a little bit before, which is we have complex computationally expensive models. How do we calibrate them to actually get a sense of the uncertainty of those systems and what their response might look like in the future? And how do we emulate them? Again, for things like running forwards problems, looking at evaluating scenarios, we need to be able to run these faster, especially as we start to couple them together, but in a way where the actual infrastructure impacts are reflected accurately. The second is, what do the impact dynamics look like, and how are those associated with the drivers of risk? So how do we categorize what different risk regimes look like? What are the failure mechanisms? What are the high risk mechanisms? And what are the families of conditions under which we might see a particular set of risk, cascading risk propagation? Right. The example that I'll use to motivate that is the example of Hurricane Yuuri, Winter Storm Yuuri, which was ultimately not that as extreme of a storm as it could have been, but it was mostly a failure of planning and a failure of risk identification and assessment that led to that cascading failure. And so how do we actually look and say, well, these are the ways in which risk might propagate, because that's how we know how to target interventions that can improve results. And lastly, how do we choose scenarios? So this is important for a number of reasons. First and foremost, communication and decision making. So I remember talking to somebody from the US Army Corps of Engineers, as part of their climate resilience group, and I remember her saying that she can't bring a PDF to a congressperson, a probability distribution function. She can't bring 6 scenarios to a congressperson. She's lucky if they'll pay attention to 2. Right? They want one proposal that they can make a decision on and one scenario of how that will perform. That's it. And it's not that much better if you go to more local, decision-making bodies. This is just it's difficult, and they really want a hard proposal and an idea of what to do. And so that's a very difficult problem. How do we do this and sort of choose a few scenarios that are illustrative in a way that actually reflects the range of what might occur and the types of mechanisms that might occur? And so I'll start talking about calibrating models. So one thing that we know is that it's harder to calibrate models that are more computationally expensive, especially as the number of parameters increases. So this figure here shows, these are a few models of ice sheets. So CESM is an Earth system model that's much more than just ice sheets, which is one reason why it takes as long as it does. But this model here, DACE, that's just a model of the Antarctic ice sheet. It's a very fast, a couple of equations. BRIC is an emulator that couples a bunch of different sea level rise things together. PSU 3D ice is an actual 3D model of ice melting and rebuilding in the Antarctic ice sheet, so that's a very physically based model. And like I said, CSM is a full Earth system model. And the idea is that, if we're thinking about not parallelizing, because none of these models are inherently parallelizable, algorithms like the Metropolis-Hastings algorithm are not, in of themselves parallelizable, then you can't really calibrate these models. As we start to get more expensive, the more physically realistic models. Right, which means you can't really get a sense of what those uncertainties might look like and what the uncertain responses. So you can operate down here in the emulator world, right? Or we can find more clever ways of trying to resolve these, because there's things that will be captured here that are not captured by the emulators, right? So there's always a trade-off there. So this is focusing on the PSU 3D ice model that I showed, that we had before. And the idea is that there's sort of 11 really key parameters here. There's more than that, but 11 that actually the results are kind of sensitive to. And there was a paper in Nature that looked at this model and said, I'm going to use a Gaussian process emulator to emulate the results. And you can really kind of get up to 3 or 4 parameters with a Gaussian process emulator, at least the family of Gaussian process emulators that they were using. And if you do that, they got these blue curves here. So in 2100, you're looking at something like, in terms of the Antarctic ice sheet contribution to global sea level rise, minus 0.2 to 0.3 meters, much higher in 2300 to the extent that you trust the model going out to 2300. But if you actually calibrate with all 11 parameters, and this was the result of, this was the PhD thesis of a statistics grad student who's now a professor at George Mason, Ben Lee, to come up with a parallelized implementation to do the calibration. You end up really dragging out that tail, right? The tail areas get much bigger as a result of choosing more uncertainty and more parameters, right? And that affects your hazard projections. It's going to affect your decision making, right? If you think that you could get up to a meter of sea level rise from Antarctica by 2100, that's very different than if you think you're only going to get a third of that, right? In terms of what the hazard looks like, in terms of what cities might be impacted, in terms of whether it's worth certain certain defense mechanisms or mitigation. The other thing is that as you get more and more parameters, as we get more and more complex models that are coupled, right? As we start to couple and have feedbacks, interactions between these parameters make it difficult to identify what are the key parameters that we really want to focus on. So this is from a recent work that looked at a very simple integrated assessment model. So this is a model that looks at how is population changing, how might that change the economy, and how does that translate into changing emissions. Very high-level model based on Bill Nordhaus's DICE model. So there's two kind of families of these independent integrated assessment models. One is the sort of top-down model, which is very stylized, highly aggregated. The other are the bottom-up models that the IPCC actually uses a little bit more. Right? But both of these families of models are used in different types of decision-making contexts. And in this case, we wanted to use a really simple model that we could really stress, we could calibrate the historical data and really stress test in terms of looking at the uncertainty in the projections and sensitivities. So we did a global sensitivity analysis. And the main thing here, it's not super critical what the individual parameters are for the purpose of this talk. But the basic idea is that the green dots, the size of the green dots, when you can see them, that is the first order sensitivity. So that's if I just change that one parameter by a certain amount, how much of the variance does that explain in the outcome? And in this case, the outcome is cumulative emissions over the 21st century.
So is it relative sensitivity or absolute? Sensitivity to absolute change or relative change?
It's absolute change.
Absolute.
Yeah. And then the blue lines are the second order sensitivity. So this is a global analysis. So if I covary two parameters, how much additional variance does that explain? How much variance does that explain? So for example, if I covary capital stock depreciation with total factor productivity, the initial level, that is a pretty thick blue line, so that's a pretty strong interaction. And the total sensitivity, so all of these global interactions, combined, that's the purple. And the thing that's most striking, at least to me, about this is that if you only look at the first order, you would get things like, the emissions intensity of this is essentially natural gas type fossil fuel, the rate at which new technologies penetrate, and not too much else. This is the emissions intensity of coal, coal-like technology, a high emitting fossil fuel, and that's about it that you would see at first order. The population stuff doesn't end up mattering. A lot of the economic stuff isn't as important to first order. But once you do the global analysis and you actually look at the interactions and the coupling between some of these parameters, the economic stuff really starts to dominate. Right? And there are some parameters that have, like the growth rate of total factor productivity, that have no first order sensitivity of note that's statistically significant, but it's actually the single most important term in total. And these are things that you have to be able to understand those sensitivities, to identify that those parameters are important. You have to actually be able to run a model often enough to do this type of sensitivity analysis. Which again, if your model takes 6 to 12 hours to run, you can't do that. Right? You just can't run it enough to expose these parameter values. So the second we start to tightly couple models and tightly couple components of models, all of a sudden even deciding what parameters do we want to focus on, becomes really challenging. So this requires, again, emulation, but again, there's sort of a chicken or egg problem here with how do you decide which things to emulate, right? But that means you have to be able to build emulators that you can actually vary that and get a sense of, what are you actually capturing. So that's a major challenge for its, going forward. There's been a lot of work done on that front, largely because of this recognition, but there's still a long ways to go, especially as, again, models get coupled. We don't actually still have a great feel for how to trace uncertainties through coupled models, especially as we get feedbacks, because the uncertainties just start to compound. Right? So how do you trace the impact of particular shocks if you're also looking at how other uncertainties propagate at the same time? Right? This is a really outstanding problem that we need to figure out how to deal with. To know how a particular impact or a particular scenario might have, what exactly is it affecting? These two have sort of lumped together because they are, in some sense, kind of related, and also because I don't really have a good example from the literature of either, which I'll talk about in a second. But first, the motivating example about cascading failures and how can we actually anticipate different types of risk regimes and dynamical regimes is Winter Storm Yuuri, as I mentioned earlier. So this caused a cascading failure of infrastructure in Texas. This is from a report from the University of Houston about what types of impacts that surveyed Texans see during the storm. And so a lot of people, difficulty getting food and groceries due to the weather and due to shortages. Loss of electrical power was one. Internet, power's going out, you're gonna lose internet. Loss of drinkable water, difficulty getting bottled water due to the grocery shortages as well. Spoiled food, economic damages, those types of things occurred a little bit less frequently, depending on how quickly power was restored to a particular location. But there are a wide variety of impacts in different parts of the infrastructure system that occurred due to this one storm. But actually, Yuuri wasn't that extreme of an event. You might think that, okay, it's an unprecedented event, you can't really blame anybody for not foreseeing what impacts it might cause. But actually, a bunch of researchers at Rice did a study pretty shortly after and found that actually the 1989 storm was worse. Right? So that's an event that had occurred historically. It actually didn't cause the infrastructure stress that Yuuri did. And there are a couple other events. There's a 2011 storm, 1951, 1962, 1983, that kind of were also extreme. Right? So Texas has had these extreme storms before, but for some reason it seemed as though they were caught flat-footed when Yuuri hit. And this is really because they didn't properly identify that what those vulnerabilities were to an extreme winter storm and how they might ripple through the system. So one thing to note first, wind and solar were not the cause of the problem, despite what a number of people have claimed in the aftermath. Wind and solar dropped low. Occasionally they went below the extreme low forecast that ERCOT uses for the winter season. But really, they say about 2 gigawatts. Wind and solar never got below 1.8. And in general, on average, they were contributing above 3 gigawatts throughout that period. So they were above what ERCOT plans for. The bigger problem is that ERCOT forecasts only having 4 gigawatts down for thermal maintenance. Thermal plants that were offline because they needed to have maintenance done, when 14 gigawatts were actually offline for maintenance. So that's 10 gigawatts that weren't available when their sort of resource adequacy plan for the winter called for 4 gigawatts. And often ERCOT gets praised for that, how savvy they are for figuring out that you want to make sure that you have reserves available for the summers to do your maintenance in the winter. But obviously that reduces your resilience if you get hit by a big winter storm. Another is that after the 2001 event, or 2011 event, which again was a lot less extreme, that also caused smaller scale problems with the gas and electricity sectors. And there was a big conversation about, okay, we need to winterize these. And then nothing happened. Right? So there was no push. FERC has a recommendation that everybody winterize wind turbines and gas pumps. But because ERCOT does not extend outside of the state of Texas, it's not actually regulated by FERC. They can actually make their own decisions independent of that regulatory body. And that is something that Rick Perry stressed as a positive, in the aftermath of the storm, saying that Texans would rather be without electricity than have the federal government get involved in their system, for better or for worse. Another thing is that Texas buildings are incredibly energy inefficient. Texas ranks 29th in the country in terms of energy efficiency. The other thing that makes this infuriating, to some degree, this failure, is that this was not a sudden, unexpected storm. This Arctic front was seen approaching for days, before the storm actually hit Texas, before the event actually occurred, but there was no communication. So people weren't prepared, they weren't able to bring plants online that had been taken offline for maintenance, that could have been brought back up. That just wasn't something that was done. And then Texas is not connected in terms of transmission to the rest of the United States or to any other part, so they couldn't get electricity from somewhere else when the natural gas system started to fail. So it's, all of these are things that if you actually had been able to think through and resolve and look at what might cause cascading failures in the system, you could hit several of these vulnerability points, and maybe you have enough resilience then to not have gas and electricity and water shortages. So this is where I would like to have an example to show how we can do this, and I don't have that. And this is really a place where we really, we really need to work really closely with people who understand dynamical systems and how to model dynamical systems. So, we may have a complex model, right? That means we're relatively limited in the number of runs that we can use. So we need to be smart about how we design, how we use those runs, how we sample from the uncertainty space. We also need to be able to determine what are the state variables that actually matter, right? What does the state space look like, and what do the state transitions look like as you move the system forward in time and expose it to different forcings or different changes in policy? What do the risk transmission dynamics end up looking like? So if you have risk of some part of the system going down, what are the probabilities of that moving forward as a function of everything going on, right? The state space, the forcing, how does that look like that's going to occur? And so we can think about modeling this in, like a network, right? Where you have different state transitions, as edges of the network, and then what do the risk transmission dynamics look like? What are the regimes that say that, okay, these are the points where you're vulnerable to this being triggered, and here's how it's likely to propagate through the system so that you can monitor and intervene if need be. And then, again, clustering into regimes that are kind of representative and characterize what those risks might look like. Right? These are really important steps that we don't have an example of how to do this in models that are complex and coupled, and also subject to large-scale uncertainty, external uncertainties.
How difficult would it be to get the data that you need in order to build such a model?
It depends. So you can actually, depends on the part of the system. So a lot of water utilities actually work relatively closely with some people. So Pat Reed in civil engineering works pretty closely with a bunch of utilities in North Carolina and Florida to do some of the modeling about their risk and how to identify when they need to build or expand reservoirs. Surprisingly, ERCOT is one of the more open to working with academics to allow them to model things. They just don't seem to listen when academics say here's the vulnerability in the system. But they share data pretty reasonably. CAISO in California does. NISO here in New York is actually quite good at that as well. So it really depends. Now then if you start talking about behavioral data, and you start talking about, well, how do humans respond to things and how does that shift, then things get a lot more hairy. It becomes a lot more difficult to collect a lot of that data. And that's where it becomes really tricky. You need, then identification of good proxies becomes really important. But that is definitely a challenge when it comes to calibration, is gathering certain types of data. And unfortunately, this is the sort of thing where insurance companies actually have a lot of the data that would be useful, but for, there's reasons why they don't necessarily want to make that available, especially if you're doing open source research and you're not willing to sign a non-disclosure agreement. So then that also raises another question, which is not something I wrote here about, what are good methodologies for creating synthetic data sets? If you have a proprietary data set that can't be released, can you extract the really key statistical features of that data set and generate a data set that looks similar for the purposes of academic research? So this is something that has come up in some of our collaborations with Los Alamos National Lab, where they have models of all of the infrastructure in a city like Norfolk, Virginia, which is very sensitive because of the big naval base, and is also very susceptible to flooding because it's sinking. But they can't release that to most people because they're worried about what happens if somebody targets some of the power transformers and substations. So they have a hypothetical city that is not unlike Norfolk, Virginia, that they are willing to share with people out who don't have security clearances. So that's another sort of thing that's not sort of core to the issue, but actually is very relevant for academic research. Is how do you get the data? How do you respect privacy and these other constraints that you may have with people who have this data? And then the last thing is scenario discovery. As I mentioned, you can't go to a decision maker and say, here, I've got 4 different probability distributions of what might occur and 20 different scenarios for each of those to illustrate different points. And here, now go make a decision. Right, again, you're lucky if you can get them to listen to one. that says you have to spend money on something. So how do we identify those key scenarios, right? And this is also important for something like, if we have an expensive model, how do we know what scenarios to run, to run them against? So this is an example looking at the shared socioeconomic pathways, or the SSPs. So these are the scenarios that climate models use to generate what emissions pathways may look like in the future. So these are the scenarios, and what impacts might look like. So these are the scenarios of how is population shifting, how is the economy growing, what does that mean in terms of energy costs, and there's 6 of them, right? So there's debate about whether it's even worth that exercise given the probability of any one of those 6 being right is 0. But in principle, they're chosen a priori. They're not based on model runs. They're sort of saying we have a set of scenarios that are. I should have put this up as a plot, but there's sort of this matrix that says here are challenges to adaptation, here are challenges to mitigation, and they just sort of picked scenarios that seem plausible at each of those corners and in the middle of that. So, for example, this SSP5 here. Is the scenario in which we keep burning fossil fuels like crazy, wealthy countries get wealthy, so there's low challenges to adaptation because you need to spend money building levees and doing whatever, but you're not mitigating because you're burning fossil fuels left and right. SSP1 is the sort of kumbaya future where we get really serious about sustainability. We stop burning fossil fuels, we spend money on adaptation when it's needed, there's low barriers everywhere. The world is just a richer, healthier place. And the others all fit in. SSP2 is very common because that's the business as usual idea where it just sort of, we just keep trucking along the same path. But it turns out that when you pick scenarios ahead of time for a really complex, high-dimensional system, you miss things, right? So this was a large ensemble experiment that was done here at Cornell. With one of these complicated bottom-up integrated assessment models, where they looked at what happens if we just, instead of having these clean narrative scenarios, right, where, again, the kumbaya scenario, business as usual, et cetera, in reality, that's not how history works, right? Things don't evolve along these clean narratives. We read them back into history. So what happens if you jumble up these scenarios, right, and kind of just run a large ensemble of different combinations of things? And so the red things here are what happen if you impose a really low carbon tax, because these models need some type of carbon tax to constrain emissions, because they're all based on economic optimization. So it's all based on prices, so without a carbon tax, there's no reason to shift away from anything. And the blue dots are the cloud where you have a higher tax. So this is the y-axis is radiative forcing in 2100, and you get you don't get that high tail when you impose a higher tax. That's not too surprising. And the policy costs, if you look at what could the GDP have been on the baseline versus what is it with the imposition of the tax, because again, there's no sort of economic feedbacks or anything here. It's just sort of, well, you could have just not invested in this, but you're spending more money on it. You get higher with a higher tax. Not terribly surprising given the assumptions of this type of model. But the revealing thing is that these little dots here are where the SSPs fall. So this is where they're constrained to hitting particular targets. So this is 6.0. If you know anything about the climate scenario literature, RCP 6.0 or the Concentrated Pathway 6.0 is a pretty common scenario that gets used. And the purple line here is RCP 4.5. So that's 4.5 watts per meter squared. That's sort of the low levels of mitigation scenario in terms of the current sort of understanding of them. And what happens is we actually don't get very much of the range of behavior, right? The spanning of outcomes, we're actually pretty limited in terms of what range do we get and where are the clustering. If we look at these scenarios and we look at what happens with a low tax, you only cover anything. SSP5 is the only thing that hits that sort of cloud. That's not, the second you deviate from any of these specific pathways. And you underestimate quite a bit of what the economic damages might look like and what those scenarios could be. And there are some pretty interesting scenarios out in that tail where you spend a lot of money and you don't actually mitigate climate change all that much, as much as you think you might do so. So this is a really important question. If we can generate these ensembles, how do we actually mine these for the scenarios that do capture whatever quantity, the variation in whatever quantity is of interest? right? How do we find those ranges of scenarios that capture that range, and then that becomes more policy and communication relevant versus what we might choose ahead of time. And the reason we have just these handful of scenarios is that climate models are really expensive. And so these are the only scenarios that our global climate models are run on. So we basically have 5 or 6 scenarios of what future emissions might look like, or what future radiative forces might look like, and then they're run on like 20 or so models, different models. That's the range of climate modeling, right, for the global climate modeling, because these models are really high resolution and really expensive. Which gets us back to the question about emulation, and should we be running really high models, high resolution models to what extent, versus finding cheaper statistical methods that might capture uncertainty a little bit more. So these are all sort of areas where good mathematical tools, good statistical tools can really help us make some progress in working towards better risk assessment and understanding the impacts of interventions and what impacts might look like. For example, I have some ideas here that I don't know how good they are. Obviously there's tools from network theory that could be really valuable. I've been thinking about persistent homology a little bit in terms of getting class categories of invariance on these networks and on these graphs that you might be able to use as a clustering mechanism. I haven't sanity checked that yet, but that was just an idea that I had. But so there's ideas here that we can bring tools to bear that are totally not being deployed in the space at all. And so thank you. Hopefully I sort of made the case that this is a pretty fruitful area, I think, for statisticians and mathematicians to help, to sort of come in and collaborate with us in the sort of modeling and impacts community to kind of make some progress on these fronts. And so I'm happy to answer any questions. And for funding, this work is funded by the DOE and NSF.
So I actually want to follow up on John's question a little bit. So getting access to any individual one of these data sets, whether you're talking about water or electric power grid information or so forth, is sort of hard enough. Mm-hmm. But you're actually talking about something where you're not just saying, I focus on this one thing and all the rest of the world is a statistical model. You're actually talking about getting data from all of them. Can you talk a little bit about sort of how you even think about tackling that challenge?
Well, so I think part of it, it's not. In any case, yeah, it's obviously difficult, but I think there is at least a growing awareness, especially as extreme events occur more rapidly among some of these stakeholders about the need to do this. So one of the reasons we see electric companies and independent system operators wanting to work a little bit more closely is that, look at what happened to ERCOT after Yuuri. So I think identification of these risks, none of these stakeholders want to see their infrastructure systems fail, right? That's a lose-lose scenario for them. And so I think, at least in terms of the conversations that we've had with people, we've been able to get access to some of the Western interconnection, actual physical data. Obviously there's a non-disclosure agreement and you have to actually simplify it to use it in academic research, but we've gotten access to that. We actually have quite a lot of access to our partners at PNNL with the hydropower system and the reservoir system data in Washington State. So there are times in which you can do this, and there are times in which people are more guarded, right? Working with insurance companies, for example, is a pain, not surprisingly. So it's a challenge, but I think it's one that, especially as the financial risks get larger, for some of these infrastructure failures, people are more likely to partner to try to figure out what are things that they could do to prevent or to minimize their financial risk. Ultimately, it boils down to money more than anything else. Yeah.
Could you say something about, there's a kind of a split of modeling philosophies here where you have kind of us that want a high fidelity something or other. And then there's Senator whatever who wants like a deterministic solution. And somehow they're not going to trust high fidelity model that we like So somehow, I mean, is there a divide here, or is there a way to bridge that policy perspective?
Yeah, I mean, there's definitely in the modeling community, right, a huge divide between a push towards higher and higher resolution models. So the question is, how do you use computational resources, right? You can sort of think about the split that way. One is, well, I can just, if I have more powerful computers, I can just model more processes at once, right? I can just do more and more high resolution modeling. That's a direction that quite a bit of the climate modeling community is going in, for example. But there is also well, instead, what if I make simpler models and I just run way more versions of this? Yeah.
Right. So, go ahead and finish your answer to his question.
Okay. And I think the point is that there's trade-offs, right? So uncertainty models that are better at capturing uncertainty are probably going to be biased a little bit more in terms of, you're not going to get the best estimate out of them because you're not resolving as many things, but you're going to actually get a sense of the uncertainty. Now, on the other hand, we know that all models are wrong, as George Box put it back in the 70s. So should we actually trust a high-resolution model with parameters that were sort of chosen by hand or by eyeballing certain things? And I guess I don't have a good answer to that. I think the point, though, is to say that there's an ecosystem out there, there's a way to balance these things. You can use some of those high-resolution models to calibrate some of the emulators and surrogate models. But you're completely right. The challenge of how do you reduce this down to a deterministic option or a couple of options for decision making is a really challenging one. And that's where we really need good scenario discovery options to be able to find at least what are the most relevant ones, because that best guess is probably not what you want to use if you're actually thinking about what the risk might be.
But I think. Sorry, go ahead.
One of the hardest things I think in this sort of context is assessing low probability, high risk events.
Yeah.
Even in the case of climate and the IPCC reports, if you go back in history, it's only the last IPCC report that has taken seriously the threats from melting of polar ice. Mm-hmm. And you run the models, and if the models give you results that are outside of the consensus range of how things are likely to happen in the future, then you tend to discard those as being not realistic. Mm-hmm. Because the consensus is it's not going to happen. And so what you do in those sorts of circumstances, I think, is a really difficult question. Whatever sort of large models you're running, because as you say, they're expensive to run. You can only make a few runs relative to things. And if there are risks that correspond to tipping points or regime shifts, whatever term you want to use, then there's a tendency that this is not something that the models have been tuned to recognize and deal with. Mm-hmm. But that's really what you're trying, that's one of the essential things that you're trying to get hold of.
Yeah.
And I think that the technology for doing that is something that really needs a lot.
Yeah, so I can speak to this a little bit in the context of the ice sheets, because that's something that I've been working on a bit, and I have seen shouting matches at AGU, at the American Geophysical Union meeting, between people who believe that Antarctica can disintegrate, the Western Antarctic ice sheet can disintegrate relatively rapidly, and people who don't. This is something that gets people in the cryosphere world very agitated, to some degree. And like you said, you're completely right. The IPCC tends to be very conservative in terms of what upper tails it will consider within the consensus view of what can occur. What we have found, so there's a paper by a collaborator of mine, Tony Wong, in 2018, that actually found that you can get at some of this with an emulator type model that looks at paleo observations. So you bring in paleo observations for calibration, not just observations going back to the 1800s. And actually, it turns out that you can't explain the paleo data without accounting for some of those faster dynamics. And so I think there's sort of thought experiments like that and calibration experiments like that can help to shed some light on, that's the sort of thing that I think somewhat moves the needle a little bit in terms of what might be acceptable or what might not be. But ultimately the IPCC is a political body in addition to a scientific body, and so they're making certain choices for political reasons. But you're completely right that this is the main challenge, is that we need to be able to run models and resolve uncertainty enough to get at those low probability events and determine what is the level of risk that are associated with them. Without that, we don't really have a good grip on what might occur. And a lot of these mathematical challenges are sort of getting at that, is how do we do that in a space where, the raw models, the high resolution process models are very computationally expensive, and when we start coupling them to each other, it gets even worse. Yeah.
So, 2 questions in one. One is a maybe math version of this. You told us about the difficulties in deciding what kind of models and what level of resolution. But is there also a serious debate about the risk measures which should be used?
Yeah, depending on the context. So a lot of times, especially in the US, it boils down to economic damages in terms of official decision making. So cost-benefit analyses are required for any type of regulation. The U.S. Army Corps of Engineers has to do a cost-benefit analysis before building a levee. In Europe, like in the Netherlands, for example, they use a different measure where it's not economically based. It's based on what's the risk of loss of life.
I might have not formulated my question carefully enough. So if there are optimization decisions based on your uncertainty quantified models of risk, what is being optimized? Conditional value at risk, quantile?
Yeah, it depends on the framework. So a lot of times it's expected value, but sometimes it's tail risk. So with flooding, it's always 1 in 100-year events. And trying to minimize that occurrence. So if you build a levee, that manages that flooding level. But that also varies around the world. In the Netherlands, when they were using that type of reliability measure, they consider 1 in 5,000 years, right, in terms of how they want to protect Amsterdam. In Vietnam, because there's just a lot more rainfall and flooding, they use a 1 in 50-year standard that they try to avoid. So it really varies depending on the specific context. And then when it comes to other types of things like the electric power system, they're just focused on money. They're just trying to provide the least cost. That's the only objective that factors into electricity system decision making.
But under what scenarios?
Well, right.
What you were talking about once per 500 years, that sounds like value at risk.
Mm-hmm.
That does not sound like conditional value at risk, for example. How bad would it be in that worst 5%?
Mm-hmm.
So those things are not being used in decisions based on such models?
No. Not in the real world anyway. Yeah, no, it's always some threshold like that. So again, in the US, it's always 1 in 100 year. Anything beyond that, maybe there's a scenario for how do we think that will shift over time, that 1 in 100 year level, but that's all that the US Army Corps of Engineers and most other bodies care about. And that's entirely because that's where flood insurance is required. That's a pure artifact of the National Flood Insurance Program and how it's, and that choice of 1 in 100 years as the threshold by which you need to buy insurance. Those are fundamentally tied together for whatever reason, why the value was chosen, which is possible. But yeah, so it depends on the context for what that threshold is and how far into the tails do they want to consider in terms of the risk management. And then if you start talking about things like extreme heat, right? There's no real mechanisms for thinking about that and incorporating decisions based on what that might look like, other than possibly what is the impact on something like electricity use, right? That's where something like extreme heat gets factored into decision making about how should you operate things at that point. So there's no real consistent governance structure about this.
So we're at the half-hour mark, so I'm going to declare victory and Thank you for a very interesting talk, and I'm sure that we can do more Q&A.